All right, hey guys, and welcome back to another AP Physics C video. Today we're going to be deriving the velocity as a function of time for a sphere that is falling with an initial velocity when the drag force starts to act upon it. And also the drag force will be a little bit different than normal, where we'll have B, where B is a positive constant, or you can call it beta, where the drag force is beta plus kV, where K is the drag coefficient. So yeah, let's just jump right into it. As last time, what we want to know is we want to know our sum forces to be sum forces y is Fg minus Fd, which is equal to ma. And if you're asking why we start with sum forces, usually whenever you're deriving velocity as a function of time, you'll sum forces or you'll do something like Kirchhoff's loop rule. Um, Not velocity for Kirchhoff's loop rule. That will come in later. But whenever you're deriving velocity as a function of time for something that has drag, usually you're going to start by summing your forces. There's not really a nice, neat explanation as to why, but someone just started thinking of it intuitively and they started from there. And they knew that, well, A is dv dt, so well, I can derive a differential equation from there. So I'm going to start and I'm going to not start, I'm going to continue and sub in what I know. And the reason why I put FG, you might be saying, well, FG is down. Shouldn't it be negative? Um, it's not, because I'm going to call my positive to be the direction of acceleration slash the direction in which the initial velocity is. So a good practice is whenever you have initial velocity, call that your positive. Call the direction in which your initial velocity is to be positive. Or when you have and if you don't have initial velocity, call your direction of acceleration to be positive. But since velocity is down and what's it called? The force gravity is also down, I will call that. I will call that to be my positive y and up to be my negative y, right? So now I'll just continue. I know that the gravitational force is mg. I know that the drag force is b plus kv, and that is going to be equal to m dv dt. Okay, so now knowing that, we're going to continue with this. Oops. Okay, I spaced out. So now we're going to continue with this and we're going to distribute that negative mg minus b minus kv is equal to m dv dt. Okay, great. So now that we have that, this looks like a more complicated differential. So basically, what I'm going to do is I'm going to make a substitution, right? Well, actually, before I do that, I'm going to isolate dv dt by dividing the left side all by m and the right side all by m. So the m will cancel here on the left, but this will now become g minus b over m minus kv over m is equal to dv dt. So now I'm going to make a substitution. I'm going to let theta equal g minus b over m. And I'm going to let, not beta, let's say alpha equal negative k over m. And you might be asking, well, why are you doing that? It's because if we leave this as is right now, the calculus will become very annoying to do. It'll have a lot of symbols that you'll have to keep writing over and over and over again. But I know that this is just one big constant. So if I take that one big constant and I just call it a constant theta, and if I take this constant multiplier k over m and I just call it this constant alpha, well, guess what I can rewrite this as? This will become theta. Actually, I'm going to not write negative, not write negative alpha. I'm going to have alpha be k over m. It's going to be theta minus alpha v is equal to dv dt. And now this looks a little complicated, but when you realize this is just a constant, this is just a constant, it's way easier. So now I'll multiply dt and divide by theta minus alpha v to both sides. Where is dt? Theta minus alpha v. This will cancel here, dt will cancel here, and suddenly I get the differential equation. dt is equal to theta minus alpha v dv. And now if I just integrate both sides, my dt looks really bad, it's bothering me. I want to cut that. Now, if I integrate both sides, this is looking like an easier differential equation, but you might be thinking, well, now there's going to be a plus c, you have to go through all of these loopholes. Well, no. If we just make some smart integration bound choices, then we can bypass that plus c, which usually in physics C you'll end up doing anyway. So I'll have 0 to t, because I know time is going to start at 0 and it's going to have to end at some arbitrary time t. So t is a variable. I'm basically subbing in a variable for a variable. And then on the right side, I know that the initial velocity at time t equals 0 is v naught. And at some time, it'll be velocity v. Now that v, keep in mind, like I said last time, it's really v of t, but I don't want to keep writing v of t over and over and over again. So I'm just going to call it v until I write my final equation at the end. All right, so this left side will become t from 0 to t. And this right side, now if you remember that rule for integrals that look like this, 1 over ax plus b dx. The rule is that the integral will evaluate to 1 over a ln ax plus b plus c. So now all I need to do is identify, well, what's my coefficient to my variable that I'm integrating? Well, the coefficient is negative alpha. So this integral will really just evaluate to 1 over negative alpha ln theta minus alpha v from the bounds of integration from v naught to v. And there, I just saved myself the hassle of having to do a u substitution. I should move this way over here. So I just saved myself the hassle of a u substitution. And if that didn't make sense, hopefully you can see that this bottom part is really just negative alpha v plus theta. Well, that b is theta, and that v would correspond to the dependent variable here, which would be x, and negative alpha would be a. Well, 1 over a, that gives me 1 over negative alpha. So, but if you're more comfortable with doing a u substitution, by all means, go ahead and do it. I just prefer this way because it's faster. So now this left side will evaluate to t minus 0. This will evaluate to 1 over negative alpha ln, and now I'll sub in the values that I have. So when I sub in v for, well, v, I'll get theta minus alpha v minus ln theta minus alpha v naught, because that is how calculus works. And this alpha is going to be multiplied by the entire thing. So to get rid of that pesky multiplier, I'm going to multiply alpha to both sides. And I know this 0, it won't matter. So it's basically like t is just by itself. So I'll get negative alpha t is equal to, now I want to think about the right side, is equal to negative alpha v minus ln theta minus alpha v naught. So now if you remember your rule of logs, you can remember that ln a minus ln b evaluates to ln a divided by b so long as b is not equal to 0, right? So now I'll consolidate the right side into one natural log. I'll get ln theta minus alpha v over theta minus alpha v naught is equal to negative alpha t. Now I'll raise e to both sides in order to try and isolate that v, which is the v of t that we're looking for. So now e to the negative alpha t is equal to theta minus alpha v divided by theta minus alpha v naught. Now this is a little bit more complicated, but we're going to multiply by theta minus alpha v naught to both sides, so that we can get the top half by itself. And now this becomes theta minus alpha v naught e to the negative alpha t is equal to theta minus alpha v. So now I know that I want v by itself, but I want a positive v. I want a positive and not a negative v, so I'll just add. So basically I'll just switch this by adding alpha v to both sides. And so this will just cancel, and now I get alpha v is equal to theta. So I'm just going to subtract by this whole thing and get it to, so I can get alpha v by itself. So now alpha v equals theta minus theta minus alpha v naught e to the negative alpha t. Um, I really don't feel like simplifying this, so I won't. So now, the last step is just to divide the whole thing by alpha. So alpha will cancel here, and I get v of t is equal to theta divided by alpha minus theta minus alpha v naught divided by alpha e to, e to the negative alpha t. And now we can sub back in those original values. So v of t, if I remember correctly, theta was, what was it? G minus b over m. So it's going to be g minus b over m. I should put the equal sign there. G minus b is equal to g minus b over m divided by, what was it, k over m? See, this is why this is annoying sometimes. K over m minus g minus b over m minus k over m times v naught all over k over m times e to the negative kt over m. And that is your final equation. Now you could simplify this, just don't. It's so much work. Um, but yeah, hopefully that helped a little bit, because I know that there is a question that your teacher might give you that shows up like that. But really, all I wanted to introduce using this methodology was the practice of making your own substitutions. Like, sure, you've heard of U substitution, and sure, you've heard of, maybe if you've taken differential equations, there's V substitution that you could do. Um, but really, when you start seeing that constants you can just group together into one variable and sub them in at the end, it makes calculus a lot easier, and it makes everything a lot easier. That's why we do these substitutions. But yeah, hopefully that helped you. And yeah, I'll see you guys in the next video.